Cool. So today we're mostly going to talk about things which are related to lab number 3. And so let me share my screen with you. And okay, I'm going to share my desktop. Okay, there we go. Perfect. So we're mostly going to talk about Lab 3 and sensors and other elements that you guys have in your kit. And what we're going to do is we're going to learn how to basically get data from the various sensors you have in your kit, like for example this guy, which is a potentiometer, to the TNZ, and then potentially control sound synthesis with that happening in fast on the TNZ. Okay, so basically after this assignment, you'll be able to make actually a musical instrument which is controllable based on your TNZ, and that's the goal of this week's assignment. Okay, so before we talk about the TNZ and how to connect sensors to it, I just want to very briefly remind you about some super basic electronic principles, because that's something you're going to have to use partly for this lab, and also for your final project. And just to make sure that we're all on the same page, I just want to briefly remind everyone about some stuff about electronics. So if you go in the lab, there is actually a link that you can open to a page on the CCRMA wiki, which was actually written by Ed Birdle, who was a PhD student at the time. Ed Birdle actually taught to 50A a while ago, and well, he was not a PhD student anymore when he actually taught the class, but now he's a professor at LSU in Louisiana, in Baton Rouge, and so he's actually the person who wrote this very, very simple tutorial here. So very briefly, I just want to remind everyone about how an electronic circuit works. Okay, so in an electronic circuit, you usually always have power supply, which is plus. Okay, and you have ground, which is minus. Okay. And on your TNZ, you have a positive pin, which is a 3.3 volt pin, and we're going to see that later today. And you have a pin for the ground. So for all the stuff we're going to do as part of this lab, power is going to be provided by the TNZ. Okay. For your final projects, it is possible that some of you might need to get power from somewhere else than the TNZ. And that's especially the case, for example, if you want to have like a lot of LEDs or something that is basically requiring a lot of power, and the TNZ is very limited in terms of the amount of power it's going to be able to provide you. So you're going to be able to power like a couple of things, a couple of sensors, but you're not going to be able to power like something like super big requiring a lot of power. So for that, you'll need an external power supply. I'm not going to talk about that today. So the analogy of an electronic circuit is basically what we see here on the left, which is a pipe with water. So this is water here. It's like a bucket with water. And so you have one side of your pipe, which is connected to the bucket, and then another side of the pipe, which is also connected to the bucket. And in the bucket, you have water. Here we have the pump. And the pump is basically what's going to be considered as the power supply, so the positive pin on our TNZ. Okay, and in this pipe, you're going to have two ways to measure the way water is actually flowing in the pipe. And one way to measure it is the amount of water which is going to go through the pipe. So that's basically going to be the debit of the water flowing in the pipe. So the amount of water flowing in the pipe. And then you also have the pressure, so like the pressure of water in the pipe, right? And debit and pressure are two different things, right? And in the context of an electronic circuit, the analogy is that voltage is the equivalent of pressure in the pipe, okay? And then the amperage, so amps basically is the amount of water flowing in the pipe, okay? And there's this formula that you can use to compute voltage in function of current, so like the amperage, the amount of water flowing in the pipe, multiplied by the resistance of the entire thing. And resistance in our case is basically going to be the diameter of the pipe, okay? So if you have a pipe which has a very large diameter, it's very easy for water to actually flow in it. So there is very little resistance. But if you have a pipe with a very narrow diameter, then it's going to be harder for water to actually flow in the pipe, and you're going to have a higher resistance. So a resistor, and so I'm sure many of you have seen the resistors in their kits. Sorry, I'm actually trying to open the resistor bag here. So a resistor, which is this component, and I think we already saw that when I gave you a tour of the lab, but basically, that is the resistor. Okay, the resistor, in the analogy of the pipe with water, is just a way to reduce the diameter of the pipe. Okay, so that will increase resistance. Okay. So usually for most circuits we're going to implement as part of this class, we're going to need power, so a positive pin, so the pump, right? We're going to need the ground, which is basically the bucket here, and it's going to be the negative pin and the ground pin on the teensy. And there is always going to be like one resistor at least somewhere to diminish the amount of current actually flowing in our pipe, flowing in our circuits. And that's what we're going to talk about today. Okay, so I strongly recommend you to just read through this page at some point. You know, like you don't have to understand everything, you know, like that's not the point here. But please just like read through it and try to sort of get a sense of how like super basic electronics works. You know, like I'm not gonna like go into too much details here, you know, because we don't really have time for that in this class, you know, and also you don't need to know a lot of electronics to achieve what we need to do here. One more thing that I want to say, you know, like this is probably like super obvious for some of you, you know, like, but I'm sorry, but I really need to remind some people about that kind of stuff here. But in your circuit, you're always going to have a positive pin, okay, so power, and you're always going to have the ground. So that's a very common mistake when you start in 250A that students have. You know, like you forget to plug the ground, for example, or you forget to plug power. And if you forget to plug one of those pins, you're basically not going to have current flowing in your circuit, and it's just not going to work, right? So you always need to have like a closed circuit between power and the ground. Okay. Do you have any questions about that so far? I mean, I know this is like super obvious, you know, like, but I felt like you guys actually needed to be reminded about that. So any questions or? Okay, I'll take that as a no. So one thing we're gonna, I wouldn't say like extensively used in this class, but one thing we're going to use probably a lot is what we call a voltage divider. And a voltage divider is what is represented here on this figure. And basically what this says, you know, actually, I don't really like this figure too much here, and I know like the Wikipedia page for voltage divider is a little bit clearer than what there is on the CCRMA wiki. But basically, what a voltage divider is two resistors in series. Okay, so say like two resistors like these guys. And by the way, in your kits, you only have 10 10K resistors, so 10 kilo ohms resistors. And I'll explain to you why there are actually only 10K resistors, because there is actually a reason for that. But if you put two 10K resistors in series, one after the other, and you power one of the resistor on one side, and then you put ground on the other side, and then you get voltage out of the two resistors, like between the two resistors, then you can actually compute the amount of voltage you're getting on V out using the formula you have here, which is Z2 over Z1 plus Z2. So those are actually the impedance of the resistor. So in our case, it would be like 10K. So here we would have like 10 divided by 10 plus 10. So that's 10 divided by 20. That's 1 over 2 multiplied by Vn. So if we put two 10K resistors in series like this, and we get currents out like between the two resistors, it's like actually dividing the voltage that we get on Vn here by 2. So for example, if you're getting 3.3 volts out of your teensy, and for one of your sensors, you only need half of that, you actually want to implement a circuit like this one, okay? And so that's a very, very convenient thing to know, you know, because very often you're gonna have to decrease the amount of current you have, like to power like a specific sensor, and that's the way you want to do it, you know. And there are many other things you need to know about electronics, but that one is actually super important because it's really useful in the context of what we do in this class. So I just want to point that out. Any questions about that or? Cool. And this is all related to Ohm's law that we saw earlier, you know, like, which is V equals I multiplied by R. You know, you can actually derive this into our voltage divider that I just talked about. Okay. So once again, just read through this, and you know, you can even like prototype some of the things that are explained here using your teensy. There's also just like read all these stuff, you know, and if you have questions, feel free to ask, of course, you know, like, but yeah, we're not going to talk more about this at this point in this class, and I just want to move on the next step in this slide, you know, like, which are actually important. Cool. Great. So as I said, we're actually going to get power from the teensy. Okay. And so at this point, you probably know about the teensy pin map, which is this thing here. Just clicked on this link, right? And this is the teensy pin map, and this is very useful if you want to know what pin is doing what on your teensy. Let me just zoom in to try to get a better view of this so that you can all see what's happening here. Okay. So this is the pin map of our teensy, and so here on the top right corner of the teensy, you see that we have a VN pin, we have ground, and we have 3.3 volts. And you can see that for the 3.3 volts pin, it says that you cannot draw more than 250 milliamps of current. Okay, if you need more than that, you're gonna have to get an external power supply. Okay, and for all the stuff you have to do in lab 3, this is more than enough. It's not a problem. Okay, but for example, if you were to try to plug all the LEDs that are part of your kit, and I think there are maybe 10 of them. And if you were to plug all of them on your teensy, that might actually be too much. You know, like just to sort of give you a sense of what this would be. Okay. So in most cases, you're going to want to use the 3.3 volts pin to power stuff on your circuit. Okay, and for your circuits, we're actually going to use we're actually going to use the breadboard, and the breadboard is this thing that you have in your kit, and so that's what we're actually going to use today. Okay, so you're going to use the 3.3 volts pin to power most of the stuff on your circuit. However, you will see today actually that there are some sensors in your kit that need to be powered at 5 volts. Okay, and so in that case, you're actually going to have to use the VN pin, which is this pin here on your TNZ. This pin is very dangerous. I already mentioned that earlier in this class, but it's dangerous because the chip that you have on your TNZ, the microcontroller chip here, operates at 3.3 volts. So if for some reasons you plug the VN pin to any other pin on the TNZ, you might actually fry it, okay? So you have to be extremely careful when you use the VN pin to not use it on the TNZ. You might want to use it with a sensor to power the sensor, you know, and we'll see today that there are actually some precautions to take when you do that. But you don't want to plug the VN pin to any other pins on the TNZ because that could actually destroy your TNZ. Okay. Great. So the first thing we're going to do now is actually plug the TNZ to the breadboard. Okay, so let me switch to this view here. Okay, so this is the breadboard. I'm pretty sure that some of you here never used the breadboard before. So I just want to first very briefly show you how a breadboard actually works and how it is wired. So on a breadboard, you have two kinds of rows. You have rows which are horizontal, like these, you know, and those are in the extremities of your breadboard. So basically, this row here, so the plus row, minus row, and then the plus row here and the minus row here. So these rows are actually used to get power and get ground, okay? And the way they are connected is that they are actually connected horizontally. So basically just like this. So basically, if you plug a wire, oops, sorry, that's that wire. So if you plug a wire to this pin here, you're actually gonna get whatever is coming on this wire to all the pins that are on this line here. And so on that very specific kind of breadboard, and it's not the case on all breadboards, but that's the way these breadboards are wired, actually only these pins here are connected. So it means that, for example, if you want to connect all these pins that we have here to all the pins that we have here, then you have to put another wire in between. And so you would do it like this, right? And so now, basically, let me try, yeah, to put it like this. Maybe it's slightly clearer. Okay, so now basically all these pins here are connected to each other's, etc., etc., etc. Okay. So in your kits, you actually have this kind of jumper wires. I'm not going to use them for this demo because I actually prefer the other ones, but they work exactly the same way as the ones that I'm using here. Okay, so if you want to take one of the jumper wire from your kit and you want to connect it to the breadboard, that's how you do it. Okay, and it's really just that simple. Okay, so actually for the sake of a demo, I'm actually going to use those just to show you how it works. So what I'm going to do is I'm actually going to get a red and a white jumper wire. Okay. And feel free to do the same as me as you're actually following this class. The rule usually is that red is for power and white is for ground. Okay, and in some cases, you might want to use black for power and white for ground. But you know, like I mean, it's this is all like kind of abstract in a way. You know, like it's more like for you to know what is what. Okay, so so feel free to follow the rules that you want. But I'm going to use here red for power and white for ground. Okay, so this is the TNZ. Okay, and so so on your TNZ, oh, actually, Doug raised his hand. Doug, yes.
I just wanted to let you know that you're, I'm not sure if it's your connection, but the video is stuttering quite a lot.
Ah, okay. Can you hear me fine though, or?
I can hear you. It's just the video of your hands is maybe a frame a second.
Okay, I think that's probably, well, it's good to know, but as long as you can see what I'm doing, it's probably fine. You know, like I don't think it's my connection. I think it's just that there are too many things running on my computer right now, and you know, on Linux, if you play like a video in Google Chrome, and actually use Zoom at the same time, because Zoom, like, I don't know, is so unoptimized on Linux that's probably the problem. I don't think it's a connection issue. I think it's just that my computer is having a hard time uh, following what I'm doing. Okay, so I'll try to go slow on that side here. As long as you can see the picture, even if it's like 1 frame per second, that's fine. You know, like I mean, that's what matters
Perfect.
is
Thank you.
that you can actually see that. Thank you. And if you miss something, please feel free to raise your hand again. You know, and just like let me know. Cool. So on the Teensy, you have, you know, like once again, if you go back to the pin map of the Teensy, on the top right corner, you have ground and you have 3.3 volts. So basically, those are this pin here, okay, and this pin here. You know, it's not the first one because the first one is 5 volts, and but here I'm only talking about 3.3 volts here, and then ground. Or is it the opposite? Sorry, it's ground first, and then 3.3 volts. Okay. So I said that I'm going to use the red wire for 3.3 volts. So I'm actually going to insert my jumper wire. That's how we call them. It's jumper wire. I'm going to insert my jumper wire in the 3.3 volts pin, right? And that's like the third pin on the Teensy, just like this. Cool. And I'm going to do the same for ground. And for ground, I'm going to use a white wire. And so I'm just going to put it next to it like this, you know, and you want to make sure that they're actually like fully inserted in the slots. Okay. So, so feel free to just like push on them. Cool. So now I'm going to use I'm going to bring the breadboard, and what I'm going to do is I'm actually going to plug the white wire to the minus black row here, you know, like so just like this, okay? And I'm gonna do the same for power, and so I'm gonna plug power. Sorry, I'm just gonna do it and then I'll show it to you. There we go. I'm gonna plug power to the positive row on the breadboard. So things should look like this, okay? So I have the red wire going into the plus row and have the white wire going into the minus row. Okay, so it means that now I have power and ground on all these pins here. Okay, so all the pins here at the top and then all the pins here at the bottom. So the plus and minus pins. Great. So it means that I can use that now to actually power stuff on the breadboard. And that's what we're going to do. That's what we're going to do now. Cool. So the next step in this lab, is actually to connect a not a photoresistor, an FSR to your Teensy. And my FSR is this big ass FSR, you know, I think I told you earlier in this class, but I get the big one because they didn't have small ones anymore when we ordered them. So yours should look like a circular thing, you know, like mine is big and squared, and yours should be like small and circular, you know, and then you have this tail here, which should just look the same as the one I have here. Okay, so this kind of sensor is what we call a force-sensitive resistor. Okay, so it's basically sensitive to the amount of force you're going to apply on it. Okay, so it's going to sense pressure. So if I press on it, it's basically going to change its resistance. Okay, so basically that kind of sensor really just acts as a resistor, and depending on the amount of pressure you apply on it, you basically change you change the resistance of your resistor. So you basically change the number of ohms of the resistor. Okay. So I'm gonna connect the FSR to the breadboard, and typically on a breadboard you connect electronic components to these rows here. Okay, so you see that these rows are actually numbered from 1 to 30 on your breadboard. And the way these rows are connected is actually vertically here. So once again, the plus and minus rows are connected horizontally, and these rows here are connected vertically. Okay, so it means that if I actually plug something here to this row, and I think this is row number 20, basically whatever is connected here is actually brought to this pin, this pin, this pin, and this pin. Okay, so vertically. So pin, in this case, A, B, C, D, and E. Okay, so vertically. So I'm gonna use the FSR on the breadboard, and I can just like connect it anywhere I want, you know. And so actually I'm gonna connect it like close to power and ground, and I'm just like gonna put it like that. So feel free to push a little bit, you know, should just fit in the breadboard, right? So you see that I actually put it like close to power and ground. And sorry, you know, this is really unpractical for the demo, so I'm actually going to use different kind of jumper wires here, which are more flexible, because otherwise it's really going to be a pain. So I'm just rewiring things the same way as it was done before, just using these wires, which are more practical. Okay, and here we go. Okay, I think that will work better for the demo. Okay, so once again, you want to plug your FSR vertically this time. You know, like you don't want to plug it like this. And so this is what you don't want to do, because if you plug it like this, basically it means that you're connecting the two pins of your FSRs together, because once again, these rows are connected vertically and not horizontally like these ones. Okay, so I really just want to put the FSR like this. Great. Yeah, Maurice?
Hi, yeah, I want to ask, is this the one?
That's the one, absolutely.
Okay, so it's not a square. Okay, thank you.
Yeah, it is the one. Yeah, it's circular. It's not a square one. Yours should look like a circle. Thank you. Yeah, thanks for asking that question. It's a very important question. Cool. So the next thing I want to do is actually bring power to the FSR. And to bring power to the FSR, I'm gonna take another jumper wire, and I'm trying to respect the standard that I used so far. So standard is to use red wires for power. Once again, you don't have to do the same, you know, like, but it's just that it's better if you want to remember what you're doing. Okay, and so what I'm gonna do is I'm gonna plug this jumper wire to the positive line on the breadboard, just like this. Sorry, this is kind of blurry. I think it's because this guy maybe. All right, yeah, there we go. So basically, I want to plug the power here on the positive line, okay, and on the same block as power here, because once again, on this kind of breadboard, not all the pins are connected. It's only like by block, okay. So only these pins here are connected together. So then I'm gonna take my power jumper, and I'm gonna plug it to any of the pins on the FSR. Okay, so it doesn't matter, like the FSRs don't have a polarity, so you can actually use any pin to do whatever. Okay, so here I'm just like choosing one of the two pins of the FSR, and I'm connecting power to it, right? So once again, power is coming from this line here on the breadboard, and I'm just bringing power to my FSR. And once again, like all the pins on line 28 on the breadboard here are actually connected to each other. So, you know, like, so that's how I actually get power from here to the FSR here, right? Cool. So the next thing I want to do is connect the FSR to the teensy, okay? Because I'm gonna want to measure whatever is happening on the FSR, and for that, I'm gonna have to use the teensy to make these measurements, right? So if you go back to the teensy pinout card, you can see on the right here that we have pins which are analog pins. It's like the orange pins, like analog pins. And you see that they're numbered from A0 to A9, okay? So A0, A1, A2, A3, okay. And so all these pins here, because they are analog inputs, can be used to retrieve an analog signal coming from an analog sensor. So here I'm going to use analog pin 0 to measure the voltage in the FSR. Okay, so I'm going to use this pin here, and so this pin is basically the last pin. Well, it's pin number 14. So it's the second pin on the right side from the bottom of your TNZ, and that's what I'm gonna connect now. Okay, cool. So all right. I'm going to use a different color now. I'm going to use, well, maybe not white because it's kind of confusing. I'm going to use orange, just like, once again, colors don't matter, but I'm using different colors so that we know what's happening here. And so I'm going to connect my orange jumper wire to the FSR, to the other FSR pin, just like this, right? So just so that you guys see what's happening here. So I have my two pins. One is getting power, and it's the red wire, and the other one is going to go to the TNZ. Okay, and it's this one. Great. So then I get the TNZ, and if you remember what I just said, the analog 0 pin on the TNZ is basically this one here. Okay, so it's the second one from the bottom on the right side. Okay, so I'm going to just connect my jumper wire to analog 0 pin on the TNZ. Cool. Sweet. So now I'm actually going to connect the TNZ to my laptop, and just going to connect the USB wire and connecting to my laptop now. Okay. There we go. And so I'm gonna like switch back to this so that it's not too disturbing. And I'm gonna start the Arduino software. You guys should know about that at this point. Okay. And in the Arduino software, I'm actually just gonna use the code from the lab because it's going to save me some time here. Okay, and I'm going to put it right here. Okay, so what's happening here? So in setup, I basically initialize serial communication. We're going to use serial communication here to basically debug what is happening on the TNZ. Okay, so it's going to be a way for us to print things on the computer that are coming from the TNZ. Okay, and so when you say serial begin, this is basically the baud rate of the serial line, or sorry, actually that's the serial port. It's not the, no, actually I think it is the baud rate. Sorry. It is the baud rate. So whatever, you don't have to think about this, just put this number, and it will work. And then in your loop, once again, the loop is being repeated forever, over and over again. What I'm doing is I'm going to read the value, so analog read, that's what I have here, on analog pin number 0. So A0 is the same A0 as the one that we saw on the pinout card of the TNZ, which is right here. Okay, so this A0 here, the same as this A0 here. Okay, and so what analog read is going to give me is going to be an integer value that I'm storing here in sensor value, and this value is going to be a number between 0 and 1023. Okay, so it's a 10 bits value, and then what I'm going to do is I'm going to print the value on the computer. And then I'm going to delay the whole operation for 30 milliseconds. Okay, so the reason why I'm doing this here, actually, it's super important that you do this, like that you actually add the delay. And so the reason why I'm actually delaying things here is because your TNZs are very powerful, and if you don't delay the loop here, they're actually going to print stuff as fast as they can, and they're completely going to overload your USB port. Okay, so to make sure that your USB port doesn't get overloaded, you actually have to delay the loop here so that only one value is outputted every 30 milliseconds. Okay, cool. So so that's cool. Then you can actually just upload that on your TNZ. So I'm uploading the code on TNZ, and you know, I was kind of stupid because I reused the code from last time, and so now it's taking forever to compile on my computer because there are all the Faust stuff which are still part of the program, and they are kind of useless in our case, but still I'm just gonna wait because in the end it should just work. Okay, great. And so so if everything went well, in your case, if you click on the serial monitor, and it's like the loop icon here on the top right corner of the Arduino software. So once again, it's right here. So if you click on this, then you're going to get this window, which is going to open. And you can see that this window is actually outputting values very quickly. And basically, the values that I'm getting here are the values that are coming from my FSR. Okay, great. So you will see if you're there at this point, you know, and if you're trying to do the same on your side as I'm doing it, you will see that if you actually press on the FSR, that's what I'm doing here. You can see that values are clipping at 1023. You know, like so here it is definitely detecting something. You know, like so here I'm not pressing the FSR, and here I am pressing the FSR, and so I'm getting values at 1023. And Clara actually raised her hand.
Yeah, I asked this question in the chat, but curious, does this need to be set to a pull down, because a pull down resistor on the other end? Because we gave it the power side, but we never gave it the ground side.
Yes, absolutely. I was going to get there. Thanks for anticipating what I was going to say. So, but it's good, you know. And so actually, indeed, it's time for me to talk about the pull down resistor. So you know, as Clara pointed out, currently something is happening, but it's not super precise. You know, like I mean, like we're getting like these super high values, and when we're pressing, we see that something is changing, but it's not something that is really usable. And the reason for that is because, as Clara said, we're actually missing ground on our circuit here. So let me put the video back here. Okay, and let me just replay things like this. So usually when you do operations on your breadboard, you want to unplug your TNZ, right? Like if you really know what you're doing, it's fine. Like you can actually leave the TNZ plugged on, but it's better like to change the circuit with your TNZ unplugged. You're not gonna like electrocute yourself or whatever, you know, because it is super low voltage, you know, like, so there is no risk in that regard. However, you can actually injure your TNZ because for some reasons, if you're you know, plugging power to ground directly without something in between, that could actually, you know, like fry everything, you know, like so whenever you change something on the circuits, you want to unplug the TNZ so that there is no more power flowing through the circuit. Cool. So I'm now going to use a 10K resistor, and those are the resistors part of your kit, and they're all 10K resistors. You know, so it's this little guy. And what I'm going to do is I'm basically going to connect that resistor to the same pin as the pin that is connected to the TNZ. And let me do it, and then I will show that to you. And the other side of the resistor is going to be connected to the ground. Okay, so on one side, I have my resistor connected to the orange wire going to the TNZ and coming from the FSR. And then on the other side, I'm actually going to connect the resistor to the ground line on the breadboard. Okay, so now things should look like this. And if whatever you're getting here is kind of blurry, feel free to actually look at the picture in the lab because it is definitely probably clearer than what I'm showing to you right now. Okay, so once again, one side of the resistor is going to ground, and it's the minus black line, and the other side of the resistor is going to the orange wire coming from the FSR. Okay, cool.
Hi, Romain. Sorry, I just want to check. It's a little unclear on the picture on the lab as well. Is it going into the same hole or just the next to the hole of the orange wire? Like C.
It's a good
25.
question. So basically, on a breadboard, as I said earlier, basically the vertical lines, you know, like, so these vertical lines here are all connected to each other's. Okay, so basically, sorry, this is still kind of unclear here. So basically, it doesn't matter if I connect the resistor like this, or, sorry, like this. Oops. Yeah. The result is going to be the same, you know, because basically all the pins on line 29 are actually connected to each other's. Okay. So that does that answer your question, Maryse, or?
Yes, thank you.
Cool.
And so even if the photosensitive resistor was higher up, like on letter A, and then the orange wire was on letter E instead, that would still be okay?
Absolutely, yeah. You know, like basically you have all these pins, like all these pins on these lines for convenience. You know, like, I mean, in some cases you might want to plug one pin to 4 pins, like going somewhere else on your circuit. And that's why you have that, you know, like we're not doing that here. Like we're only using 2 of them per lines, but yeah, you can use any of them basically. So yeah, Julie?
Does it matter like left, right for the sensor? Like your orange is going into the, I
No.
guess. Okay, it doesn't
So,
matter.
but it depends on the kind of sensor you're using. So if you're using a sensor like the FSR, which acts as a resistor, because basically the FSR is acting as a resistor here, there is no polarity. It doesn't matter how you wire things, okay? But you have other kind of sensors where it actually matters, you know, and for example, like that sensor, which is the ultrasonic distance sensor that you're going to use also as part of the lab, then there is actually an order to do things, okay? But in the case of the photoresistor, it's super simple. We could actually flip the photoresistor, turn it upside down, you know, like it would not change anything, you know, like, so there is no order for that. Cool. So I'm gonna reconnect the TNZ to my computer. And you know, like whenever you do that, you actually want to look at the TNZ, especially when it's the first times you're doing this kind of operations. Whenever you connect the TNZ to your computer, you kind of want to look at the TNZ, and if you see that there is a weird light, I know this is not like super clear, like what a weird light is, you know, like, but if you see like there is a light like turning on the TNZ, like a red light or something like that, you know, and your TNZ looks like it's actually like crying and suffering, it's like, you know, then immediately unplug the USB wire because you probably made a mistake. You know, like whenever you plug your TNZ, there shouldn't be any light turning on the TNZ. Okay, so you want to be gentle with that. You know, and as I said earlier in this class, you know, like we can give you another TNZ if you fry it, but it's going to be a pain like compared to previous years because you guys are not necessarily on campus, and yeah, so try not to fry your TNZ. That would be great. Anyway, so I just plugged my TNZ back, and and I don't have to change anything here in my code. I can just like restart the serial monitor, and now I can see that I have 0 being outputted in the serial monitor. And then if I press on the FSR, I'm actually going to get values, and now they're actually usable. Okay, and so FSRs are actually fairly precise. Like they're very sensitive. And you can kind of play with it, like to see like how well you can control it. But they're like very precise sensors, not necessarily like super linear, but they do work well for what we're doing here. So cool. So just before I take more questions, I just want to explain very briefly what the resistor is doing here. Like we added this 10K resistor, and so like you're probably wondering what it's doing at this point, and why now the circuit is actually working. So basically, the 10K resistor that we're using here is what we call a pull-down resistor, and I think there is this diagram here in the lab where you get power, you send it to the FSR, then it's connected to pin A0 on the TNZ, and then you have the 10K resistor here, which is connected to the ground. And so what the resistor is doing in our case is basically sucking all potential power going after the FSR to the ground, But whenever like there is more power flowing through this, because we basically we are pushing on the FSR, then the 10K resistor is basically not small enough to actually draw the power to the ground. So it's going to the A0 pin instead. So basically, like once again, a resistor, it's like reducing the diameter of a pipe in a pipe where there is water flowing, and so here, if we have a very narrow pipe and basically there's an even narrower pipe here, basically the water is going to go here because it's going to be like easier for water to go through the larger pipe than through the narrower pipe. Okay, but as we are pushing on the FSR, it's like we're actually increasing the diameter of the pipe that we have here, and so it's easier for power to go to the A0 pin instead than to the ground. So power is going here instead of here, and that's why we're getting these values, like so if we're not pushing on the FSR, power is actually going to the 10K resistor, but whenever we're actually like pressing on the FSR, power is going to the A0 pin instead, and it's also acting as a voltage divider here, as we said earlier, so if you wanted to change the sensitivity of your FSR, one way of doing it would be to actually change the value of the resistor you have here. Okay, so that would actually like change the sensitivity of the FSR. So usually when you have sensors which act as resistors, like an FSR and many other kind of sensors, you always want to put a pull down resistor. That's kind of a rule. Like if you don't have the pull down resistor, it's not going to work. Okay, and in the lab later, like I show you how to use all the sensors that are part of your kit. And if you buy sensors online, because the sensors part of your kit don't satisfy your needs, then usually it's very easy to actually find informations on the web on how to wire them and how to put a circuit together to actually use them, so usually this is very well documented. So anyway, do you have any questions so far?
Yeah, I do. But hydrate, please.
Yep.
So I'm getting, even though I'm not touching the sensor, I'm getting ones that sort of like periodically go into the serial port. Is that right?
Wait, you're getting what? I'm
Like-
not sure.
Like periodically it's mainly 0, but then it goes like 1
Oh yeah,
often.
yeah. No, it's totally normal. Like that's that's fine, because basically these kind of sensors, like our force sensitive resistor, they're analog sensors, and well, in fact, all sensors are analog sensors. Like at one point, like, I mean, there's very few sensors that actually act as pure digital sensors, but they are they're not perfect, and so what I'm saying is that if you're flickering between 0 and 1, and your entire range is 0 to 1023, like, I mean, it means that like you're basically like off by one value, like in that entire range. It's not a problem, basically. Especially like think about MIDI, for example. Like in MIDI, the range of values that you can use is from 0 to 127. So basically, if you were to quantize the values that you're getting here between 0 and 1023 to 0 and 127, your one would probably just become 0, and so we'll see that in many cases you need to actually do some filtering on sensors if you want to get like very stable values out of them, So thanks for asking that question, because probably all of you are gonna find yourself in the situation, where the sensor is flickering a little bit, but that's how these sensors are, and maybe it's not even the sensor itself, maybe it's just the electromagnetic field in your room, which is sort of influencing the wire on the teensy, and so this is perfectly normal, basically. Any other question?
Could you show us your monitor again? Because
Yeah.
I'm only getting 1s and 0s. I'm not getting other values.
Okay. Then it's a different problem, right? So basically, this is my serial monitor. And so I'm getting like sort of, like even in my case, I'm getting some ones, like once in a while. But like whenever I start pressing on the FSR, I'm getting higher values. So if you're only getting ones and zeros, maybe it means that you're not powering your FSR. So maybe like the first thing you want to check is that there is actually the power pin connected to your FSR and that it's properly connected. We can look at that kind of problem after class, if that's okay, because we have a limited amount of time, and maybe this is going to take some time for debugging, is that okay, Julie, or?
Yeah. Oh,
Okay.
I'll just come to your office hours. Thanks.
Or just come to the office hours. Yeah, absolutely. Yeah, that's another way of doing it. Cool. So at this point, it should be fairly straight. Okay, let me just turn off the big camera here because I feel like it's definitely slowing my computer down. And yeah, I'm just gonna disconnect it here to make sure there's no issue. Great, perfect. So basically, at this point, you can actually get the values from the sensor and potentially use them to control a false parameter. And so if you go in the next example here, and I'm just gonna like copy and paste it in the Arduino IDE here. Okay, in that example, I'm basically reusing the Faust sawtooth, that we created last time. So at this point, you should know how this works. So I'm using like a Faust object, right? And so in my case, yeah, everything looks good. Okay, great. So it's basically Faust sawtooth. There is an output. There is the audio shield, and I'm connecting the Faust sawtooth to the main output of my teensy. Except that what I'm doing then is that I'm in the loop, I'm getting my sensor value with analog read A0, okay? And then I'm turning that into a frequency, okay? And then I'm using my frequency value here to control the freq parameter of my Faust sawtooth oscillator, okay? So once again, like my Faust sawtooth oscillator is the same as the one from the previous lab, like so just go to the previous lab if you want to find it. And so here, all I'm doing is that I'm using it to actually make sound on the Teensy and control that with the FSR. Okay. So what I'm gonna do is I'm gonna replug my Teensy, and then I'm gonna upload this program on the Teensy. While this is happening, I'm gonna go get the headphones that I actually forgot. I'll be back in 10 seconds.
While Romain's away, just a quick plug for everybody to remind you that you can set up times with me one-on-one if you'd like, and we can go through this stuff together. Or you can also go to my regular office hours or Romain's regular office hours for help with any of these things. And this lecture was recorded, so you can always refer back to this as well.
Yes. Yeah, thank you, Doc. Cool. So I'm using the same circuit as before. I didn't make any change to the circuit. And so here I just uploaded this Faust program, this Teensy program based on a Faust program, which is the Sawtooth Wave program that I just talked about. Okay, and I'm just gonna increase the volume here so that we can all hear what's gonna happen. So I'm uploading this on my Teensy. Okay, so I don't know if you can hear it, but I get a very low frequency Sawtooth wave, and whenever I'm gonna start pressing on the FSR, I can actually control the frequency of my Sawtooth wave oscillator. Cool. So that's exciting because if you actually get to this point, you have your first hardware digital musical instruments completely standalone. So that's definitely a big milestone. I just want to say a couple of things about the program that we had here. So basically, what's happening for frequency is that once again, I'm getting a value here from analog read, which is a value between 0 and 1023. So what I'm doing here is what we call mapping, right? So I'm using the value from analog read, and I'm trying to convert it into a frequency value which is meaningful in my context. So I don't want to have a frequency which is lower than 50 hertz, for example, or at least I don't want to have a frequency which is lower than 20 hertz, because that would be like a super low frequency that I would probably not even hear, like it would be too low. So because my sensor value is giving me value which are below 20, I'm adding 50 here just to make sure that the lowest frequency I'm gonna get for my instrument here is going to be 50 hertz, okay? And then I'm not doing like more complex mapping, because I don't really care about the higher frequency, so the plus 50 here is only to make sure that the lowest frequency I'm going to have on my instrument is going to be 50 and not 0, okay? Cool. So another thing that that you should note here is that there is no delay anymore in the loop. Like in the previous example, we had a delay 30, and here there is no delay. And the reason for that is because I'm not using serial to print things in the serial monitor on my computer. Okay. Right now, everything is happening inside the Teensy. There is no information which is connected to, which is communicated to my computer, and so that's actually one of the good things about doing something completely embedded as we are doing here, because for example, if we were to use the Teensy as a controller connected to the computer to send MIDI messages, for example, then we would have to slow down the whole thing, you know, because of what I said earlier, like that would actually overload the USB bus of your computer. Here, because everything is happening internally in the Teensy, it doesn't matter, you know, like I can do things as fast as I can, and so I'm gonna get like super low latency because of that, you know, and so basically that little system that I have here is much lower latency than everything I would be able to do on my computer for that very specific reason, you know, because of its simplicity and the fact that I don't have to delay stuff here to actually make things questions about that example before we actually move on to the next thing. Great. Okay, should be pretty straightforward. You know, like I mean, if you did lab 1, this should be a piece of cake, basically, right? Cool. So in the lab, there are exercises, and so, you know, like it's not because we did all this thing here that you don't have to do the lab, you know, because I actually skipped a lot of things, you know, so you actually want to read the lab and you want to do the lab. Otherwise, you're going to be completely lost for whatever comes next. Okay, so please do the lab. Read the lab, you know, like read all the points. Try to do looking at the picture. It's okay, you know, like just look at the examples, implement them on your breadboard, and so please do the lab and do the exercises, you know, because they are actually important stuff, you know. So in the lab here, there's another section which is about discrete events. Okay, so what is a discrete event? So currently, in the case of our FSR, we are sending a continuous value to the Teensy, right? So it's a value that is evolving in time, you know, and it's continuous, it's changing, you know, like, so we're changing the voltage, right? Which in most cases is going to be created by a button, okay? And so as part of your kits, you have these little buttons, and so these little buttons can actually be mounted directly on the breadboard as shown here on the picture. Okay, and so you can use buttons the same way as you would use an FSR. So you could use like an analog pin to retrieve the value from the button. You know, like so if you're pressing on the button, you're getting like maximum voltage. You know, like so 1023. And if you're not pressing on the button, then you're getting 0. Okay, but this is not very smart because you know, there are a limited number of analog pins on your Teensy, and so in that case, you actually don't need an analog pin. You can just use a digital pin, and digital pins on your Teensy are basically any pins which are not the power pins. Okay, so basically all these pins from 0 to 13 can actually be used as digital pins, but they need to be configured to be used as digital pins, and that's what is actually done in this example here. So in that example, let me zoom in a little bit so that you can see everything here. Okay, cool. So here you can see that in the setup, I'm actually configuring okay, and if you do this, you're basically configuring digital pin, right? Not analog pin. You're configuring digital pin number 0, which on the Teensy is basically this pin. It's the pin on the top left corner, the second pin on the top left corner. And it's this pin, and here we are configuring it to be used as a digital pin. So once this pin is configured to be a digital pin, you can actually connect your button to it, and then you're going to use a digital read, and the digital read is just going to say either 1 or 0. Okay, so there is not going to be more off, and in fact that's what you want for that very specific case, because you're using a button. You don't need like all the intermediate value that you have between 0 and 1023. So in the example here in the lab, what I'm doing is I'm showing you how to turn your button into basically a checkbox, because if you click on the button, you're basically getting, like not pressed, pressed, not pressed, right? But what if you wanted like to use this, like to cycle through different notes, and that's what this example is doing here. So this is a melody which is coded into the example, so those are the notes of my melody. And so every time I'm going to press the button, I'm going to switch to the next note, etc., etc., etc. And so in order to be able to do that, you need to implement a mechanism, like a software mechanism, which is going to turn the value you're getting from the button into basically a trigger signal, like that just says like, okay, do this once, do this once, do this once, and so that's what you do. So like I'm just like sort of explaining you what to expect, like for the rest of the lab. So once again, there are exercises. Please do them, and I can't say that enough, like read the lab. It's super, super, super important. And the reason why I'm insisting is because I remember that last year, not everyone read that lab, and actually people were completely screwed for the following assignment because they actually missed like super crucial points here. One important thing that I want to point out in that very specific context, and it's actually explained in the lab as well, is that our Teensy is actually using currently the audio shield. Okay, so if you look for where is it? The audio adapter on the Teensy website. There is a link in the lab, so you don't have to look for it. Like you will see, that's super important, that for the Teensy 4.0, all these pins on the Teensy are used by the audio shield. Okay, so what does that mean? It means that, for example, if you wanted to use pin number 15, which is this pin here, okay, and you would like to use this pin as an analog input, for example, you would not be able to do it because it's already used by the audio shield. For sensors to your Teensy, the first thing you want to do is you want to check which pins are used by the audio shield. So for ground and power, it's okay, because you can share ground and power with anything you want, like so. For those two and this one, it doesn't matter. But then all the other pins, so this pin, this pin, this pin, this pin, you're never going to be able to use them for doing something else because they're already used by the audio shield. Okay, and this is also explained in the lab, like so. But I just want to highlight this because it is super, super, super important. And that can be a cause of a lot of weird, like you're probably not going to fry anything if you use one of these pins, but it's probably going to prevent the audio shield from. So anyway, so later in the lab, you have this section which says using the other sensors of your kit. So this portion of the lab is not mandatory, so you don't have to read it necessarily, but I strongly recommend you to read it anyway. Okay, so it's more here to be a resource to know how to use the other sensors which are part of your kit, and so for each sensor part of your kit, I'm giving you an example of how to use them. And so I'm showing you how to use the ultrasonic distance sensor, which is a great sensor. Like it's super precise, it's very cheap, And it basically allows you to measure the distance between the sensor and whatever you put in front of the sensor. So if you put your hand in front of the sensor, you're going to be able to measure the distance between the hand of the sensor. So it means if you want to implement like some kind of instrument, like a theremin type of instrument or something like that, you could actually do that with that kind of sensor. Something you might want for your homework, might want to do for your homework. Okay. I'm showing you how to use the potentiometer, and there are multiple potentiometer in your lab, and that's this guy here. And the potentiometer is super easy to use. It's probably the easiest sensor to use ever. And basically in the potentiometer, you have 3 pins. You have 1 pin for ground, 1 pin for power, and 1 pin that needs to be connected to the TNZ. And there is not even need for a pull down resistor to do this. So that sensor is like super easy to use. I'm showing you how to use the accelerometer, and so you see that every time there is a little bit of work to do, and a little bit of soldering work to do, because in all cases you're actually going to have to solder wires to those sensors to eventually use them. Once again, this part of the lab is not mandatory. You don't have to do it. If you don't have time to do it, don't do it. But it's just that if at some point throughout this class, for one of your projects, you want to use one of these sensors, that's where you want to look at, because you have all the information on how to use the sensors. Here you have the another kind of distance sensor, and that one is an infrared distance sensor. It's basically this sensor here, and it's even more precise than the ultrasonic distance sensor, and yeah, I actually really like this sensor. It's super nice. You really can do like vibrato just by putting your fingers on top of it. It's a really great sensor. Anyway, just to conclude today's class, I very briefly want to talk about the next assignment, which will be due on next Wednesday, which is April 28th. So what we want you to do is to design an instrument running on the TNZ, combining a bunch of sensors and a sound synthesizer implemented in Faust. That's pretty obvious that we were going to ask you to do something like that. Okay. Feel free to explore the various sensors which are parts of your kit. So if you want to use the accelerometer, use the accelerometer. If you want to use the ultrasonic distance sensor, use the ultrasonic distance sensor. Yeah, just use any sensors. Your instrument should involve at least one discrete element, like a button, okay, and one continuous element, like a potentiometer, an FSR, photoresistor, like whatever, just you name it, just but you need to use at least one discrete and one continuous sensor. Think about the mapping strategies you'll be using on the sensors. For example, does it make percussive sounds? Are all the parameters linear as opposed to logarithmic, for example, etc. Okay, so mapping is super important. If you actually listen to what Gus said on Monday, you'll know that mapping actually matters a lot. And this is probably what's going to determine if your instrument is playable or not. So you want to spend a lot of time, fine tuning whatever you're getting from the sensors to control your sound synthesis process. Make sure that your instrument is expressive, artful, beautiful, playable, blah, 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 as usual. And you could obviously fulfill the requirements for this assignment by using any of the code in this lab. But we expect more. We want you to be creative here, okay? And especially, we want you to think about the form of your instrument, okay? So feel free to mount all this on a coffee mug, feel free to dress it, I remember a couple of years, a student just turned his TNZ into a Furby, and feel free to turn it into a Furby, if you want to put fur on it, and put an eye on it, and maybe put the photoresistor in the eye, and when you poke the eye, it just does something, that's fine. You know, we want you like to try to do something which is a little bit more than just breadboard and the sensors connected to it. Like try to come up maybe like some kind of metaphor. You know, like try to make a toy or an instrument. You know, like try to be creative, basically. Okay, and finally, make a video as well, you know, like out of your instrument, you know, like once again, we'll be very diligent about this because we know that we're going through hard times with these remote teaching for that kind of class, which is really not optimal. Anyway, I think that's it for today, but I'm sure you're going to have a lot of questions. You know, that's what office hours are for. On Monday, I waited for people to come in office hours, and only one person came. You know, like, so feel free to come to my office hours. I know that Doug is nicer than me, but you know, just don't be afraid. You know, I'm here too. You know, I can and of course don't be afraid to go to Doug's office hours, and don't be afraid to send us questions if you have any. But do you have any questions?
Would an accelerometer be considered as a continuous input sensor, although it's digital?
It is not digital. It is not digital because we actually purposely included an analog accelerometer in your kit. Usually when you buy breakout boards for accelerometers, they are digital breakout boards. So it means that you need to have a digital connection between the accelerometer and your microcontroller. But actually, the accelerometers as part of your kit are analog. And so if you look at the accelerometer and if you look at the pins on top of it, you will see that it says ST and then Z, Y, and X. So Z is basically the voltage output for the Z position of the accelerometer. Y is the voltage output for the Y position, and X is the voltage output for the X position. So it means that if you want to use 3 axis, you're going to need 3 analog inputs on the TZ. So it is not a digital sensor in that case.
Oh, thanks. I really assumed it was digital.
Yeah, because they are actually cheaper. If you you know, like actually these are kind of expensive. Like that breakout board I think is $15 or something like that. You know, like if you get like a digital accelerometer breakout board, it's gonna be like $2 or $3. You know, like but it's kind of easier to deal with that kind of accelerometer breakout board. You know, like so that's why we actually included those in your kit. Any other questions? Cool. Well, thank you guys. And once again, if you have questions, feel free to ask them on Canvas or directly by email if you prefer. And yeah, I will see you otherwise on Monday. On Monday, we're going to talk about OpenSCAD, which is the software we're going to use later in this class for 3D printing. So yeah, good luck with your assignment, and yeah, once again, feel free to ask if you have any questions. Thank you.